Yo, all right, what is up, everyone? Welcome to week 93, building my own operating system. Thank you for joining. This week is probably some virtual memory, I think. Is what we will get into this week. I'll do a bit of a recap of the current state of the kernel, and then yeah, it's kind of an exciting week because we're sort of able to start a kind of a new topic. We were spending quite a bit of time on this bitmap allocator stuff, and that's pretty much done at this point. So I think we can kind of move on, and we'll have to figure out what is next exactly. But yeah, I think something along the lines of virtual memory, something along the lines of page tables, and I'm hoping that this will have a lot of core operating systems stuff is what we're going to be getting into. What's up, RHDWRRR? I have no idea how to say your name. I'll just call you RHD. Thank you for being the first one in the chat today. Nice to see you. I'm going to hit it with the test 0, even though I believe the chat widget is already proven to be working. Nice. So, yeah. Oh, let me post quickly in the Discord just to get people in there. All right, pings. Streaming now. Virtual memory, probably. All right, got that ping sent out. Cool. How's everyone doing today? Feel free to just give a bit of a check-in. Anyone working on any cool projects? Windows 1.0 in the house. What is up? Nice to see you. Always appreciate you all being very punctual at the start of the stream. Do appreciate that a lot. Okay, I'm just setting my windows. Yes, I know it's Catflare. I wasn't sure if you were trying to reveal or conceal your identity with a different username. But if it's all public, I'll call you by Catflare in this case. Okay. What's page tables? Page tables are the data structures that the OS uses to integrate against the virtual memory paging features of the CPU. And we are pretty much ready to start using them because now we have the bitmap allocator. So that's kind of cool. Okay. What's up, Nirajan Data? Switch from C to C++. Yeah, pretty much. I mean, the idea to use C++ has been a very long time coming. It was always my intention to use C++. And after I finished the MIT course, I started taking steps to make C++ available in my kernel. At this point, I've pretty much started from scratch with my custom kernel. And we are heavily using C++. So, and we'll get into a little bit more of that today. So yeah, nice. Cool, got 10 people in the chat. Maybe that's a bit of enough yapping for now, and we'll kind of start to get into things. Okay, clean everything out. Quick just recap of what's been going on. So let's just take a look at the history. So Yeah, this is basically what we were working on for kind of a while. This branch, it has the bitmap allocator, and let me just mostly this is the commit, and it's our new data structure slash object, and it's able to allocate frames of physical memory if given the memory map. And we even have a bunch of unit tests, which took a lot of effort to kind of like get the infrastructure available to do that, but we have it now, which is pretty cool. How long did it take you to complete the MIT course? It took me about 1 year of only working on it 2 hours per week. Because that's pretty much all the free time I have. And so if you have more than 2 hours per week, I think you could do it probably faster than me. But it took me about 1 year of doing it with 2 hours per week. And also I've heard that the one that I did is a little bit harder actually. I was doing the 2018 version because it uses x86. I've heard reports that the newer versions that use RISC-V are a little bit easier. And so maybe you could even do it in even less time. If you're using the newer version. Okay, so now my goal here is pretty much, I have this, the current state of the kernel looks like this, just to show it off. It doesn't really do much, but it prints the memory map. And that's what I was doing in this branch. And so I added a function for dumping the memory map, and it is not really that complicated. And then I am officially adding it to the kernel, adding this memory map request, and then in the kernel I just have this some code that checks that we have the memory map, and if we have the memory map, we call that function that I added in the previous commit. And this is a bit of a random change. This is all some like other random stuff that we were playing around with. It's just some other utility functions for computing the number of physical frames and other things like this. So yeah, that I don't think I really need that actually. I think I'm just gonna maybe stash those changes, and so I'm just gonna hit the capital S and stash all changes. K-main memory misc memory map functions. Okay, and so now that I have this, I'm pretty happy with the state of this branch. Util, and I will just merge that in right now. Regular merge, push. Okay, cool. So got that in here, and now we have some. Let's make a branch called next branch, because I don't actually know what. I don't exactly know what we're going to do. So let's take a look at the roadmap. But before I do that, I'm just going to make the. So we're in week 93. It is November 9th. Let's pop over to the roadmap and just check out what has happened. And so we have officially finished quite a few things. We have finished the bitmap allocator tests. We've kind of cleaned this up. Integration testing, serial driver kernel class, use ASAN, use stood source location. Yeah. What's kind of most magic enum? Kind of a random thing. Okay. SIMD. This is done using built-in FFS. So that actually was completed. Oops. Okay. So I think probably some virtual memory stuff is in order. For example, what's up, Abdullah? Thank you for joining. Yeah, like migrating away from the bootloader page tables. This is kind of a question mark for me, and I'm actually a little bit nervous about trying it because I don't completely understand it, but maybe that's a sign that it would be worth looking into. I don't know, some other ideas like writing a serial driver. Let's just kind of go ease into the topic of paging and virtual memory setup, I suppose. Yes, so and let's just quickly review some of the notes from the other. Oh wait, this is another thing, the static bitmap size problem versus trying to make it dynamic. That is actually maybe another interesting idea. Currently the bitmap allocator uses a hard-coded bitmap size. And that puts a maximum, like a hard maximum on the amount of physical memory that can be managed. And maybe we want our kernel to be a little bit better than that. A bit more dynamic. I mean, it's really not the most important part, though. I think I could live without that. Yo, what's up, chat? What's up, Creeper? What's up, Raj? What's up, Digitalized? We out in the Safari today, exactly. But yeah, kind of a sunny situation. I'm just not at all super gray here, but yeah, no, we're out here in the Safari. So, yes, sir. What's up, Rajneesh? Damn, we got chat popping off right now. This is very unusual. Okay, I'm gonna take a note of that for the roadmap, but I think no, let's just look into virtual memory. That's what's feeling most alive. Oh wait, where did that go? Dang. Okay, I'm just gonna make it card. So alive, interesting, challenging. I don't exactly know the map problem. Can we make it dynamic? I don't know. For the moment, we're just going to keep hard coding the bitmap size. Okay, let's talk virtual memory and see what... we were discussing this a few weeks ago. We were discussing this when... Oh, right. I'm going to get the break timer going just in case. Okay, so... we were discussing this a little bit ago, and so right now when the kernel is running, it's running off of page tables that have been created by bootloader. So, okay, Rajneesh, starting point resources. Great question. I have kind of a random list of stuff here. Really, all I did was just follow this free online MIT course, which taught me pretty much everything I know. And that is just what I did. We are using page tables created by Leemine bootloader, and they live in a particular place. Maybe also time to whip out the old Leemine protocol document. So glad my kernel won't have to deal with virtual memory. My brain still gets messed up with 411 page tables. Oh, and no virtual memory kernel. That's interesting. It's because your embedded board like doesn't have paging or something like that. I mean, yet the no virtual memory design is also kind of an interesting way to do it. review. So let's just reference the documentation to understand a little bit better about what it is and what we're trying to do here. No TLB, interesting. Okay, I need to search for the word page tables. Okay, the bootloader page tables are in bootloader reclaimable memory, which I think is exactly what is here. And so the question is, do we need to take action about this? So this is the state of things, and basically the bootloader just does a lot of stuff out of convenience for us, including completely setting up virtual memory. And the question is, okay, the kernel takes over now, and what do we do? Do we keep using these page tables, or what? And like, why or why not? And there apparently are some reasons why you do not want to keep using these page tables. What's up, Avery? Thanks for joining the stream. Cheers. And the reason, so we were talking about this with NSG last time. Safety usable entries in bootloader need to set up on page tables. Okay. In our discussion last time, interesting. So with the page tables, it's not a great idea, because if you ever wanted to reclaim the memory in the bootloader reclaimable region, you would not be able to very easily do that, because you would still be relying on parts of what is living inside these kind of random bootloader reclaimable regions. So a safer option is to kind of take what's living in there that is like important and copy it and migrate it out into the usable normal regions. And then once you have migrated everything out of the bootloader reclaimable region, which is sort of meant to be kind of like a temporary zone for data, then you can basically just mark all these regions as free and available for use by the OS and start like overwriting them and having them participate in the global, like in the broader physical memory management of the system, basically. So that is a reason why we might want to migrate the page tables out of the bootloader reclaimable regions. Okay, so now what I'm thinking about, okay, so we can migrate the page tables, that sounds okay, but there are some other things though, and maybe we can see them in the docs, but page tables are not the only thing that's in this bootloader reclaimable region. We also have the response structures and the stack. And so I'm going to search for the word stack. Okay. So I'm just going to try to document a little bit of what is all in the bootloader reclaimable region. Oh, we got the man himself in the house. NSG, what is up? Yes. Yeah, I was thinking of trying to get into this topic. Yes. And since you are the expert, maybe you could help me out. So my plan was basically to try to understand and move away from the bootloader reclaimable data, like migrate the page tables into the usable region and kind of switch over to them. And to be honest, I actually don't really know what I would do after that point. I have some understanding that there's more virtual memory setup that I want to do for the kernel's address space, but specifically, I'm not completely sure what I would need to do, and probably I'll just kind of go back to JOS and see if there's anything in JOS that I could copy. But basically, I don't know, that's maybe a bit for the future, but for the moment, I was just sort of thinking of going with this bootloader reclaimable thing. What's up, Raj? I started following you while studying from scratch, building a mini kernel in Python. Whoa, that's cool. How do I keep track of everything? I keep track of everything in this like insane whiteboard, which looks kind of cool. I don't know, has kind of grown quite a bit over the years. She's quite informative. Thank you very much. I'm just kind of yapping into the internet. Anyway, yeah, so migrate the page tables anyway is sort of like the main idea. And to be a bit more informed about how to do that safely, I'm trying to figure out what reclaim. Yeah. Okay, let's check out the word reclaimable. Okay. Okay, all responses and associated data structures. So that's one thing to watch out for. Before we would potentially get rid of the bootloader reclaimable memory, we need to copy migrate everything out of there. So bootloader, okay. Responses, bootloader, page tables. Number 2. GTD register is loaded to point to a GTD. Oh, okay. Okay. Now that is a little bit of a question mark for me. The GTD. I mean, it's been sort of a little bit of a little while since I had to think about that, but maybe it's not so bad though. I mean, we're in 64-bit mode, and so GTD is not really used anymore, and it might be as simple as copying this data elsewhere and pointing the GDT register to the new one, and like that's it basically. I don't know, something like that. Stack. Now that is kind of interesting. Our stack is in the bootloader reclaimable memory. And so that, I don't know, that means that we will need to switch to a different stack. And that is actually, that's probably, that would be an example of a virtual memory change, I guess, or part of the virtual memory setup is, as part of our kernel virtual address space, we're going to need to set up our own stack. And actually, that is kind of familiar from JOS. The way JOS worked was there was this initial boot stack that was used from the entry point, and we kind of ran on that stack while we were doing a lot of initial setup, and then we, after we were finished, we dropped into user space and started running the first user space program. And then from that point on, the boot stack was no longer used, and that the stack that was used by the kernel is actually like the interrupt stack. And we would set the IDT descriptors to point at the interrupt stack. And so from as soon as user space started, the kernel would pretty much only get execution in response to syscalls and interrupts, and both go through the IDT, and both ended up just using the interrupt stack. So VM to do set up kernel stack. That sounds kind of like a mature thing to do for a kernel rather than running on this boot stack. Oh, what's up, PO Trek? We got you in the Twitch chat. How do you learn the internals? I wonder if my resources command works in Twitch. I think it wasn't working the other day, but you go. I think AI can be helpful. Absolutely, yes, I do. Absolutely, and I use it in the streams a decent amount, actually. Okay, so stack, right? Let's keep going. Stack, reclaimable. These are guaranteed. There's some like alignment and whatever. Yeah, okay. HHDM input. Okay, that's confusing, but it's not really relevant because we're not using EFI. Okay, so DTB, this is only relevant for like ARM or whatever. We're not using a device tree. Cool. What's up, Tugra? Nice to see you, dude. Also, what's up, Andrew? Mom, get the camera. Mom, get the camera. Okay. So this is our complete list of all the things that live in the bootloader reclaimable memory and all the things that we need to be very careful to migrate out if we are ever planning to actually reclaim that memory. And okay, most of this sounds fairly doable to me at this point. So what would be so maybe time to sketch out like a little bit of like a roadmap. So our end goal, right, is we have migrated everything out of the bootloader reclaimable regions that we need. We have reclaimed the bootloader reclaimable memory, which concretely looks like created the page tables, migrated the response data for future reference, migrated stack or something to production kernel stack, migrated GDT, or no, not GDT, not GTD. Wow. That was it, right? So stack responses, page table, GTD, stack. Okay. I think I have some duplication. Yeah, okay. I'm gonna delete this one. Okay, cool. So that's kind of the end goal. Okay, so migrate page tables. We are running on page tables allocated in the usable memory. Okay, and then so starting point, and this is here we are right now with literally absolutely nothing done. And so the question is, how do we get to our end goal? And I think, well, clearly it's going to be a step-by-step kind of thing. And I think probably I'm just going to ease into it. I think migrating the response data is a nice way to ease into it. Or not, or we could go straight for the page tables. Honestly, this is the scariest thing for me. So maybe that, honestly, the response data is like a little kind of, I don't know, I'm not too scared about that, but I don't really know what this means. So maybe that's good to just get immediately out of the way. GTD and stack can kind of come later. Kernel interrupt stack. Okay. So migrating the page tables. All right, you know what? I'm just gonna go ahead and hit this this break. Will take the 20 seconds. Feel free to join me for a quick stand up, get some water, whatever. All right, cool. So migrate the page tables. And so let's talk a little bit more about what this means. So in general, yeah, we have this general concept of this general idea that the kernel is running on some page tables when it receives control from the bootloader. And their specific layout is undefined as long as they provide the above memory mappings, which are specified here. Pop open I don't know if this makes it a bit easier to read. Entry memory layout. Yeah, so these are the details about exactly what kind of virtual memory layout is provided and implemented by the page tables. And the confusing thing is, like, it differs between the different versions. I'm using revision 3, which is specified right here. Let me just quickly remember how this stuff works. The executable gets loaded at some address. So there's a few concepts here, and it has been a little bit while. Executable load address is one concept. There's the HHDM, which is a different concept. These are, I think, two of the key concepts. And if we even look at the output of the kernel, we can see that I'm currently printing out a couple of these things. So we have fizz base, vert base, HHDM base. Vert base. Mohammed just stumbled upon the video. Wish you best of luck. Thank you very much, Mohammed. Okay, let's refresh on what these things. So vert base, this vert base, where does that come from? So fizz, right, exe adder request, HHDM. And so, okay, so these two things are coming from the exe address request, which we can full address can check out right here just for a recap of how this works. I mean, it's not really that involved. You are able to ask for the physical address that the kernel has been loaded in and the virtual address, basically. That's sort of what we're seeing here. This like F blah, 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 8 blah, blah, blah number, which is sort of reflected memory layout. Or I guess no, we already had here. So this is what they're talking about here. So there's this one thing where there's one mapping for placing the kernel at this address in virtual memory. Okay, that's number one. Okay. 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 Alongside the loaded executable. So this was number one. Now we get to like 2 or more. So, and alongside that, there's a couple more things. And I still do find this a bit hard to read, but basically what I'm understanding here is that at the HHDM start, which is this, we get the physical memory linear mapping of all physical memory, basically. And there are a few details about what actually is mapped into the HHDM, and they are specified here. Usable, blah, 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 blah. So we get these. Okay. And I think that's kind of it. I mean, is that all it says? The reason it's more, I just want to understand this is I want to have a sense of what the page tables we're going to migrate look like. Like, is it a lot? Is it going to be like a bunch of like all these different regions, or what? And so far it does not really look like that much. It's pretty much two conceptual things, the executable and the HHDM. The HHDM is going to be kind of fragmented, and so because we're using version 3, and so it's like going to be missing, like things are just not mapped in by default. Like the reserved ones are just not going to be mapped. The bad memory is not going to be mapped, and so there are going to be some holes. And so we actually you said the mappings according to the machine state at startup. Yeah. Going to the machine state at startup. I'm sort of, okay. Basically, I'm interpreting that just to mean like you just copy the ones from Lemine. Sort of what I'm planning to do. No, it's not cursor. This is VS Code. So I don't know. Let's anyway. So yeah, this thing is going to have some gaps, and we can kind of anticipate what it's going to look like. Just capture this again one more time. So we can sort of anticipate the gaps. It's going to be kind of fragmented. We're not going to have these reserved regions. We're not going to, and that's pretty much the only thing. Okay, so what is the first code to write then? We basically just need to do a bunch of mem copies of page tables. If I am getting this correct, mem copy all the page tables, then set CR3 or whatever to point to the new set. So that is sort of what I'm You're not copying anything at all. Okay, so clearly I have a massive misunderstanding. I don't really get how you could not copy things, because I thought the whole point was to get them out of the bootloader reclaimable region. Am I kind of wrong about that? Or what? Because that was sort of my understanding, is that like this data is living in the bootloader reclaimable region, and eventually we're going to basically clobber all of that data that's in the bootloader reclaimable region. So then, okay, right. New page table, got it. Functions for mapping and unmapping, word, okay. Same as the machine startup state, and switch to that. And so what do you mean by machine startup state? Because machine startup state, right? Like, so are you talking about like what Lemine sets up? Are you talking about this basically? Because that was sort of my idea, is just to like, rather than manually setting up docs mappings that are set up, right? And so my idea was, instead of manually setting up all this, I was thinking of just copying the page tables, because the page tables already have this, or maybe I'm not thinking that through clearly. So it's not worth the hassle. Interesting. Okay, I want to just. It's not worth the hassle. Okay, you're saying it's harder to actually copy the page tables than it is to simply re-implement the memory layout. Okay, I think I understand what you're saying. And let me think. I just want to think about that, understand it a little bit better. Yes, to copy, you would need to you need to traverse the entire thing. I'm not sure that's hard though. I mean, right, yeah, I mean, yeah, so yeah, what I'm saying is that, yeah, we would need to implement like a deep copy of the page table tree. Okay, maybe we start writing some of this down. So there are, okay, question, how to migrate the page tables. Number one, NSG idea. Allocate new page tables and manually re-implement the same layout that Lemine provided. And this was my idea. Deep copy the Lemine page tables. And yeah, so this is it's not going to be completely fully trivial, because the page tables are going to point to other page tables, and those physical addresses need to be rewritten to point to the new one. So, right, we'll need to alloc new pages and then rewrite rewrite the various phys adder pointers to points to the new ones. Okay, now what's going on over here? And so allocate new page tables, implement functions for setting up mappings, etc. Use these to manually implement the same layout that Leon provided. Interesting. Sup Ismail. We're deep in a debate right now. Where'd my water go? All right. All right. Yeah. What to do? I mean, obviously NSG has quite a bit of experience in this area, and I don't. And I think what I want to do, I understand conceptually here, and I'm just sort of curious what this would look like, to be honest, the deep copy. Oh, shit. Is the chat broken? I feel like I see it up to date with the latest messages, so are you not seeing that? Yeah. So I would just be curious to learn for myself firsthand how painful this is. And I apparently I've been warned, but I'm sort of just curious what this would involve. Maybe, but yeah. Okay, probably it's time to get out the Intel manual. I want to have a bit of a visualization of the page tables before I keep going. So let me pop that open. Oh, if you look at XV6, okay. Dang, I wish I could read this language. It's crazy. I don't know how to get to the table of contents anymore. Okay. I am curious. Okay, let's just take a quick look at XV6. Do I have a local copy of XV6? Check the AMD manual as well. Right, yeah. I'll just take a XV64. Oh, what? I've never heard of this. I've never heard of XV64. Okay, let's just, for a quick reference, let's just take a look. Also, XV64, what is... And we're saying vm.c. And what's it? Copy UVM. Given a parent process's page table, create a copy of it for the child. That is exactly what we want, actually. And apparently NSG is putting us on to like this other OS. But yeah, okay, interesting. And what does it do? Given a page given the page directory, I suppose, for every what? Yeah, for every, wait, conceptually quite simple. Walk through the entries, allocate physical page, copy, new page, then map. Okay. All right. Quick 20, be right back. Okay, wait, so, what is this doing? So I is 0, I is size. I like don't exactly understand this. And I bumps at page, so I is like an offset or something? Or no, I gets casted to a pointer, and it PTE should exist. To be honest, I really am not understanding this code, but I think, and it's like verifying that there should be a PTE and it should be present. And then it pastry calls walk. It's all based on walk. Interesting. Mem move, and so we allocate a page, I'm guessing, and I was watching the stream with a 20 minutes delay. Okay, and we copy what? We're copying this thing and then mapping this thing. Okay. Okay, well, let's think about this for a quick second. So, truthfully, I'm not really understanding this because I don't really understand what these functions do, but I think I conceptually understand the basic idea. And it also sort of seems like this kind of routine is useful anyway. Sub hello code. Pretty good, how are you? Looks like your caps lock key is broken, by the way. Not sure if you knew that. Yeah, okay. Okay, I still would like to whip out the docs. In a program that I can actually get table contents. I think this is what I want. Yeah, we're also in 64-bit mode with the different levels of page tables. So formerly we were operating with like this kind of setup. page directory and page table entries. And now we got this kind of thing. Okay. Okay. So I sort of see what NSG is saying, that maybe it is kind of annoying to implement this deep copy kind of thing. But I don't know. Okay, well, in any case, I think we'll probably end up implementing some of the same fundamental code in either case. And so maybe there's just a bit of a starting point we can reach, or we can just start with some kind of basic abstraction for dealing with page tables. And yeah, it's going to be responsible for perhaps managing a set of page tables. Okay, maybe we can start to sketch something out right now. And okay, the question is always, so where do I do this? I'm in the kernel. Maybe it would be cool to unit test this eventually. So maybe kernel lib would be better, but then we need to like mock the hardware. Maybe we just start doing this in the kernel right now and switch it over later if we want to do that. Okay, so what can I do to start off with? I can just start off with I'll just make a new file or class. Yeah, I'll just make a new let me just see, what kind of setup do I want here? Kern. Okay, we're just keeping it pretty simple right now. So I'm just going to duplicate this file, and I'm just going to call this something like, I have no idea. I'll just call this address space.hpp maybe v address space. And I'm going to delete everything. And what could we, like, what is this going to really be about? So over here, we're just going to start sketching some code out. We're going to need to get the current CR3 to current page tables. Then then allocate new page PML4 table, I suppose. And then maybe there's some, I don't know, some kind of function, etc., that copies the existing CR3 page tables into the new set described by the PML4 table. Something like this. And maybe I'll just go ahead and make a copy of this just for reference in my directories. Git clone. Oh, what? Oops, x86 public. There we go. Just to have this around in case, say no, in case we want to reference this function. Okay, cool. Right, so go back to here. Where's my code? Okay. The general concept. I'm just going to start coding a little bit. So let's just start super easy. Let's get the old CR3, right? We're going to do the read CR3. So auto CR3 equals read CR3. And maybe we really do not have x86.h. Okay. And just log it. Or, yeah, 3. And returns even 32. So let's just see what this looks like. Wow. Not 64-bit mode. Oh, interesting. Yeah, so I copied this x86.h from JOS, but this is like 32-bit. So honestly, yeah. How, like, okay, so obviously CR3 is a 64-bit register. Okay, let me just try this. So what? Okay, time to get some help. Please make this work for 64-bit. EAX. Okay, you know, I do not. Is it the move L or move Q? Okay, that is an example of something esoteric that I do not know. Oh, and then I need to, okay. Okay. So that is pretty clearly a physical address in one of the, in like this, F9. Okay, we're in this region right now. So it's an okay, so the page tables are in this final bootloader reclaimable region. And oh man, we have 23 people in the chat. This is like very embarrassing because I don't really know what I'm doing. Okay, so but clearly, so we got our CR3, and it is a physical address in a certain region. Right. Okay, so now, I mean, maybe it's just, maybe, yeah, it's probably a good idea just to have some basic functions for like manipulating things and mapping things into memory. So let's just sort of see how that might work. I'm really just gonna kind of sketch it out, but make this v address space thing. It looks difficult. I don't know if it's that difficult, if I'm just being kind of slow right now. Okay, so okay, so let's just say we want to make a v address space. This thing is going to need to allocate memory, so it's going to depend on the bitmap frame allocator. Right, and let's okay, so we're going to depend on a bitmap frame allocator, and I made the decision to call this thing allo, because that sounds kind of cool. And let's also say it's going to take up the address of some kind of page PML4 table, maybe. So let's just say we're going to allocate the new one and then pass it in here and kind of get ownership of it. Yeah, like what would that, so would we pass it as a physical address? I'm not quite sure, but I'm just going to do that. PML4 table, something like this. And we're going to store the PML4 table, something. Sort of kind of guessing here. We're going to stash the allocator and the for table. Right. Okay. So now, now we can try something. So now we can map to bitmap frame allocator. I hate typing that out. Okay. Bitmap frame allocator allo given the memory map, right? That's how you construct this. And then now we're just going to PML for OP PML4 table equals allo.alloc, right? And we just allocated OPPML4 sub Saran. So we're gonna allocate that, and let's just we're going to just print out what we got. And so, I mean, I'm going just like very slowly here because I still don't really know what I'm doing, but just see what that looks like. Man, already time for another palm tree break. Be right back. Feel free to join me. Okay, so here's what we're seeing. Our CR3 is living here. And we just allocated our first frame, and that's straight up right here. That is the first possible free frame on the system. Never considered making OS. What does it take to code something like this? Takes blood, sweat, and tears, and a lot of looking very stupid on the internet. How long do you think you are from completion? Probably a couple lifetimes if I had to estimate based off of the rate that I'm going. Yeah, no, I don't know. I don't really think about completion for this project really. Okay, so whatever. Very basic stuff, but kind of inching along here. So we've successfully allocated something, and then now we can actually would autocomplete those for me. The address space. Okay. There's space, the adder space, and we're going to pass it the allocator and the OPPML4. Any source material you are using. So I'm not using this anymore, but for the longest time I was using this course. And now I am not using any material, and I don't know how well that's going, but yeah. Okay, so now I guess the idea is interesting. What, you know what, actually this probably need to mem set this to 0 or something. So what I'm sort of envisioning though is, like, you can imagine this kind of abstraction for managing a virtual address space, and you can imagine that there are maybe some methods like map and unmap or something like this. I might want to reference JOS actually, just to kind of refresh on how they did it. Just gonna open the old JOS 2. Okay. So quick inspiration break. JOS. All right, there were a couple functions here that were useful. Map, unmap, remap, flag. Yeah. Right, so that sounds like a reasonable API. Like JOS, you would pass in like the root page directory, and there were some like functions you could call. Pagedir walk basically allowed you to query for a particular virtual address. And this was sort of like this high level function that was used. So that, I mean, that's a useful primitive to have for sure. Basically, given just a random virtual address, do whatever it takes to look up the page table entry for that address, including possibly allocating and mapping it if needed. So that's one example. Maybe I'll write this down. No, I mean, so whatever. So pagedir walk is one example. That's a function we used quite a bit in JOS. Okay. This is completely different. Pagedir walk, page insert, page lookup. I'm just going to screenshot this just for reference. Page insert. Okay, so what's the deal with page insert? Here, this is mapping. This is like mapping, right? So given a physical page, we're trying to map it into the address space at a particular virtual address with some permissions, right? So pagedir walk is sort of this querying function. Page insert is like mapping. So what's page lookup? Returns the page. Pagedir. So this was like sort of a slightly low level function, pagedir walk, which was used by page lookup, which is a sort of a thin wrapper around pagedir walk that slightly different. Instead of returning the page table entry pointer, it returns the page info. And so all it really does is it does almost nothing. It just like calls pagedir walk, and it just does a conversion from the page table entry and converts that into the corresponding page info struct, which manages the represents the actual physical frame basically. And then page remove. What's up, Sir Drippy 6969? Thanks for joining the Twitch chat. Okay, then like this stuff is like not that important. So as NSG already had wisely said, map, unmap, remap. So that would be another suggestion for the interface. I'm just gonna capture that for the old notes. And so that's one style. Okay, so that was a good bit of a refresher for me. Ooh, okay, so I mean, I actually sort of like the idea of like this query kind of function. I mean, I could literally implement the same semantics as the JAWS API, but I'm not completely sure I want to do that. So what would be a good starting point? Probably, I think probably a good starting point would be maybe just working on trying to map, just like map something in maybe. I also just had this realization that it might be kind of interesting to be able to unit test some of this. Like, it would be kind of cool if in my unit tests I could instantiate a v-address space and just like call some methods on it to like map something and query it and whatever. I do believe that would be pretty useful, but it requires a bitmap frame allocator. And in the unit tests, I would want to be able to swap this out for just like some kind of stupid allocator that's backed by malloc or like something like this. But yeah, this like will get quite tricky though, because this thing is going to need to do all these conversions between physical and virtual addresses, and all of that stuff will need to be mocked also potentially. So yeah, that's like a little bit tricky. Yeah, sounds like something I might invest into later. Curious of what that would look like, but for the moment, it might be a bit much. So yeah, what's up, JB? What's good? All right. Sir Drippy, this stream is all about trying to make an operating system very, very slowly, but consistently, and without really knowing that much about this. So yeah, now trying to make an operating system in C++, in like modern C++, and looking kind of stupid in the process. So yeah, what's up, Blech? No file system around virtual memory right now. Okay, what's like a reasonable little first thing we can try to do? We can try to, let's just try to, I guess, map something, right? And what is the map API going to look like? Maybe we just pretend let's call it VA. I don't know. So va.map, and let's say we're trying to just like, we're trying to map it's going to be very similar to page insert, right? We're trying to map some physical frame into some particular virtual address, and probably we'll need to specify some permissions about that, right? In the visual terms, this is the physical frame, and we're basically just trying to, the operation we want to perform is, we're given this frame, and we're just like, and we're given some kind, and we're given the linear address. We're given this thing, we're given this thing, and we're like, hey, virtual address space, do whatever it takes to like make this thing point at this thing, which concretely under the hood is going to mean like routing all these arrows like all the way through the chain. And it's going to mean, I mean, not all, like not literally every area, but like it's going to mean like routing all these important arrows that point to the next thing all the way down through the chain, all the way to here basically. And it's also going to mean allocating these larger blocks if they do not already exist, because we're trying to thread this like chain all the way like through the thing. So that is the conceptual operation here. And so you could imagine an API, and there's an interesting thing. So this page info, we don't really have this concept of a page info yet. Do we need one is the question. Or is it enough just to pass an aligned physical address? I don't know, but I don't know. Let's just see. So let's just sketch it out a little bit. Call this PML4 table. So, and this is also kind of interesting. We need to be zeroing things out probably. I mean, the VA address space could also allocate its own. Yeah, I don't exactly know. It doesn't really matter. Let's just go with something like this quickly here. So can we go for the std fill? And okay, this is going to be interesting because now in order to zero out the memory, we need to convert it to virtual addresses. And we actually haven't needed to do this yet. So memory, here's where we get to our functions here. Subsid, killer hack, killer programmer, thank you, my guy. Yeah, okay, so yeah, now we're trying to get into this code that we haven't touched in a while. And actually there's quite a bit of old stuff here from JOS, actually, this FISMAP base thing, that's like completely not true anymore. And you know what, actually a lot of this info is going to come from the Lemine requests, in particular the HDM base, right? And so this is like kind of interesting actually. So what do I really want here? Again, I can imagine some kind of abstraction which can be used to convert between physical and virtual. and it, I don't know if I'm overdoing it with the classes in here and stuff, but I'm just going to sketch it out like this. So what is the name? It's going to be our sort of like this conversion memory converter. I don't know if that's a bad name, but we are going to store, it's going to be the virtual address of the linear mapping, which I'm just going to store as a uint64. No, uint. No, I mean, it really could be a void. I'm gonna call it, what's the name? It's like the, I don't love this HDM terminology because it's kind of opaque. I'm gonna call it the linear mapping base because I believe that's a little bit clearer. And this is really going to be a very simple kind of thing. Fizz to vert and vert to fizz, something like that. Again, not really sure if I'm overdoing it here, but and so fizz, we're going to take a const fizz adder, and fizz to vert is simply m plus p adder, right? We just add the offset, and now there's going to be a 20-second palm tree break. All right, be right back. Okay. So now we probably have a error that I cannot read because it's in a language I don't understand. I mean, it's obviously, no, it's like obviously some kind of type error. You know, I need to cast it or something like this. So here's the part. Actually, p adder, interesting. Let's point u into pointer t. And I'm kind of not doing a very nice thing by using these C casts, but you know what, something a little bit like this, and then we got the vert to fizz, and it's going to be exactly the opposite. We're trying to do a subtraction, and again, int pointer t. Oh, wait a sec, but wait a sec. Trying to get the physical address of a given virtual address, right? Wait a second, I'm just thinking through that for 1 sec. So we have the linear mapping. It represents all of physical memory. So any physical address, we just add it to the offset. We get the mapping there. And if we have a particular, yeah, no. Right. What am I thinking then? Why? Yeah, no, obviously you cannot just do that. Or can you? No, if you have a virtual address in the linear mapping range, you can do this. Let's adjust it, right? Why would I think this? P-adder, right? Why would I think this is possible? Yeah, and so this doesn't work in arbitrary situations, but it works in specific situations. So you can give it an address in the linear mapping. Yeah, this only works for addresses in the linear mapping. But if you happen to have an address in the linear mapping, then it's a trivial subtraction. Right, and so this thing that I'm, this like class that I'm working on is not meant to be really an arbitrary conversion. It's just meant to kind of encapsulate the linear mapping conversion. So maybe I can name this better. I'm going to call this linear mapping, linear map converter. I don't know if that's clearer. I'll call this the linear map. Okay, and so there's probably some kind of like to do assert v-adder is in linear mapping range, something like this. Wait, in this case, they're both void stars. And so really the cast is going to be, I'm going to cast it to a fizz, but wait a second, fizz adder is actually a class. And so we need to construct a fizz adder and 64. Probably cast this, I guess, something like this. But now, what's the problem? Damn, what is... The expression must be a pointer to a complete object. Are you kidding me? Well, I don't know. Subtracting void stars, maybe that's not really nice. So we're just gonna okay. So there we go. I'm just going to quickly ask the A, please clean this to, please use C++ casts here. And I guess it's static cast probably. I always usually go with static cast first. You know, that's interesting. I'm just gonna do it to use better casts. And likewise, I'm just gonna flip this around a little bit. Okay. Right, so, and then assert, what's the assertion actually? So the basic assertion is so the v-adder is greater than the linear mapping base, first off. And assert that it's less than something. And so the question is, how long is the linear mapping? And the linear mapping is, we get that information from the memory map, right? And so the linear mapping is going to end on like the last region that is not reserved or whatever. So if we wanted to, we could actually parse the memory map, find the start and its endpoint, and then pass that into here in order to be able to assert this better. And maybe that's like kind of a cool idea actually. So I don't know if I'll do this right now, but parse the memory map to find the endpoint 2, then we can assert better that a v-adder is within the linear map. The reason I'm using this word linear map a lot and not HHDM is because the linear map is the terminology that the Linux kernel uses, and so that. But you know what? People also call this the fizz map, which I actually think is a lot more intuitive. So I'm going to rename this to the fizz map converter. But we'll call that fizz map adder converter. Maybe that's a little bit clearer. And I'll call this the M fizz map base. Cool, okay. And then, so yeah, then assert that the adder is less than the end, right? So could add some type that captures the start and end, something like this. But anyway, so I just wrote like a bunch of code and I don't know if it compiles, but the reason I was getting into this is because I needed it here. I just wanted to zero out the page, the frame that I got, and I actually haven't needed to like access physical memory yet so far, because everything that I've been doing so far is just passed by limine, which is already in virtual memory. So this is the first example. This is the first example of a time where I'm actually interacting with kind of fresh physical memory that the only place it exists is in the fizz map. The range would be start plus highest page frame number. Times page, true, yeah. So, you know what? We can, yeah, let's just do that. So, okay, maybe one thing at a time. I'm kind of like jumping into like a bunch of different buckets at once. And so we had, just to quickly capture it, we're trying to prototype a v-adder space class, starting out with just adding a simple map function. Then we kind of went into a bit of this rabbit hole. It's like, oh, we need to zero out the PML 4 table frame. Oh, we need to convert to v-adder in order to zero it out, which led to the creation of our new fizzmap adder converter class. And now it's like, oh, we could like assert the end if we wanted to. And so we're kind of diving deep into the rabbit hole. Before we like dive into here, let's just finish up maybe like this key point, because we kind of did this already. So now, and I mean, this would be something to put in the kernel lib. This is just pure math basically, so I don't really see a reason why this could not be in kernel lib, and we can unit test it. Move to kernel lib and we can unit test this. That is something doable. But okay, for the moment, let's just kind of test it the old-fashioned way. So now we're going to instantiate. So first of all, this is kind of a mouthful, but so first of all, we're going to instantiate. Do we have memory? We do have memory. Okay, we're going to instantiate our phys map adder converter converter class, and we're going to pass in this thing. So this is, why is this right? Okay, so now it's complaining that we are asking for a void star here, and this is a UN64T. I mean, it's kind of a good question. Do we really need this to be a void star? All we end up doing is casting like the hell out of it anyway. So, like maybe not. I'm just thinking of directly storing a uint pointer t or something kind of crazy like that. And I think that makes this go away. All right. Yeah, okay. But what about this? So now we got some problems with trying to compare uint pointer t. Trying to compare things, so it's a problem. All right, I just want to ask a quick question to the chat. Actually, just curious, is anyone learning anything right now? I'm just completely curious if this is like new stuff to anybody, you know, like using C++ in classes right now, because just kind of curious where you all are at in terms of like your knowledge of stuff, but just kind of curious about that. So feel free to let me know if there's any particular thing that I'm doing right now that's like kind of interesting. So yeah, okay. Anyway, so we're kind of making progress. So now we have our converter, and now we're successfully able to try to use this to convert this physical pointer, which maybe I'll represent in the name. How would I? It's like the crazy thing is it's an optional physical address. Call it fizz, I don't know, kind of a chunky name. Right, so I'm gonna go ahead and then we'll get it's going to be a p viator, and I'll rename that later. We're gonna use the converter to go from here, and we're just gonna pass in the op fizz this thing, right? And we're just gonna log. We're just gonna do our logging. So I'm gonna log out and just to kind of slowly see what these things are. Right, I'm just gonna panic immediately just to check this out. So we're just gonna print out again these physical addresses and stuff like this. Let's just run that kind of quick. Undeclared identifier. Oh, interesting, did I not? assert.hpp. Okay. Nice. Let's take a look at that. That looks pretty good, actually. So, so this is related to this thing. So we can just see, I mean, it wasn't complicated math or anything like this, but we can see that we allocated the first frame from the system, which is in this usable range. And now we're just trying to convert it to its corresponding virtual address in the HHDM. And in the documentation, it was talking all about how I don't know where was it talking about this, but like talking about how the HDM is at this FF8 blah 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 number, and we can just clearly see that our adder is like exactly that thing, just with this offset added to it. So yeah, that's working, and that means we can now actually do this mem set or whatever. Is the PML4 table. Right. So now we can just go ahead and do that std fill, I believe it's called. Except how do you use std fill? I think I need the fill underscore n. Get the first size and value. So it's going to be, so we're going to start from the PPML4 table. It's going to be k page size, and we're going to put in the 0. So I think that might work. Okay, now we're having some compiler errors because it's a void star, so we probably need to cast this to char star. Probably get that out of there. But cast. Okay. Since we're in C++, let's use C++. Okay, so a little bit of a chunky, wordy situation. Okay, so now we officially zeroed out the frame, and we could continue with whatever we were trying to do. Let's just run it to see if anything crashes, because you never know these days. But it looks like nothing crashed because we successfully hit the panic. So that's kind of cool, I guess. I sort of just want to see it crash, actually. So let's just pretend we had a bug. What would a bug be? Let's just try to write to somewhere that is not mapped. So let's just return like null pointer from this. And so now we're just going to try to this thing is going to return 0, and that's 0 is going to be here. And we're going to try to write a page of zeros at the 0 virtual address, which is not mapped into the virtual memory. And so calling p2v on REV address, calling p2v on a, you're talking about right here? Oh, you mean for the error or something like that? This is a physical address, right? Bug scenario, you mean? I see, okay, yeah. Yeah, that would, right, that would crash too. Let's just, I'm just gonna go ahead with this null pointer. I think that should serve the same purpose. I'm also gonna kill the palm tree because, oh man, that bug has bitten you before. Okay. I wonder, wait, just kind of thinking about that. I wonder if there is an assert that can help with that. So calling P to V, right? So that's, what kind of assert, can we do assertions here? So we can maybe assert that P adder is low and within the fizz memory range as specified by the memory map. I think that would actually be kind of a cool assertion also. Kind of a similar thing here. We could assert that, yeah, in my case, I don't know what types you're using for these things, but I actually am using kind of this strong type for a physical address. Although it's sort of like implicitly convertible from uint64t, but it's not implicitly convertible from a void star. So if I tried to pass a void star, like if I tried to, let me actually, this is kind of a cool example. So let me just comment this out. So what's the example? It's like I just got this PML4 pointer, right? This is the virtual address. Let me do that bug scenario again. So we're going to call this thing, and we're going to try to pass the PML4 table, right? That was the suggested bug situation, and we can see that we start to get a compiler error because this is a void star. It's a kernel virtual address, but this function does not allow passing in a void star. It takes a fizz adder type, and so I actually, in order to really produce that bug, I would need to cast this to a uint64t or something like this, or directly construct the fizz adder. And so actually, I think it would be a bit harder for me to like accidentally have that bug, I think. So squiggly line with the error that I cannot read come in handy. Okay, but let's kind of just zoom in back in here. We're going to pass null pointer, which is obviously a bug, and therefore we're going to like sort of like null pointer dereference as we write the zeros. We do not have any kind of interrupt handling set up at all, so I would believe that it's going to like triple fault or something like this and reboot the machine a lot. And let's just check that out. No. Okay, so let's just yep, check that out. We are boot looping with the triple fault. So that is exactly what I expected. So cool. Okay, so we're sort of reaching a bit of the end of things here. But wow, this like turned into kind of an interesting stream actually. What would be next? I mean, yeah, I don't want to get too deep into anything yet, but so we have successfully sort of allocated a new PML4 table, zeroed it out. We're passing it into this new abstraction that we're making in order to manage a virtual address space. And we want to do something like this. So now it's going to be like, we're going to allocate OP. I need a better naming convention for this. So now we're going to allocate a new frame and maybe write data into the frame. And then just for fun, let's just say we want to map that into a particular place. And I don't know what kind of address it would be. We can like just choose a cool address like hex 8000 or something like this. Or maybe we map it at like the 1 megabyte mark. I don't know. That's kind of a neat thing. And wait, what's going on? So right, and so now let's say dest vadder or something like this. So now we got our destination, and so I'm just going to pass that in there, and then we're going to pass in the OP frame, right? OP frame, something like ranges should be good for this. What's up, Moose? Maybe, I guess I'm not quite really seeing it quite yet, but I mean, yeah, we're going to be iterating over some containers and stuff, so maybe, yeah. And right, so obviously this prototype doesn't exist yet. And we're going to take a const phys adder, right? And so here's the more of the prototype, and we want to I don't know, validate alignment, etc. And then now we're going to try to map in the frame at this vadder. And what errors? I don't know. Something was already there, maybe? Or do we just overwrite it, or what? I don't know. What does JOS do? Page insert. So here we got the, okay. Map it somewhere. Right, so the JOS semantics are that it removes, it like overwrites an existing frame that is there. Right, so yeah, that's interesting. And so query for a given VA, map a given frame at a particular VA, and free the frame at a given VA, something like this. Question marks everywhere. Yeah, I don't know, still not completely sure if I'm really organizing this in a way that makes sense, but I think this code looks like kind of cool. Got their converters, and I mean, actually, so what we're going to need to do is our v address space is going to need to do conversion, and so it's going to need converter, right? And this is, so we're going to need to declare, we're going to need the memory.hpp. Why? Okay, I'm not completely sure. Map adder converter. Why? What's These are both here, both just straight up in this directory. So what could be going on? Okay, so I think that, I don't know if that was like a Clang debugger. I don't even know what, do I have a syntax error? No, what? No matching construct. Okay, so now we're over here. I'm gonna pass in the conv. Is conv a reserved word? No. Okay, we've got, dang, something's bugging out. Oh, I'm gonna reload the window. Okay, check it out. So we have a virtual address space, and what I'm doing might appear a little bit odd, but I'm trying to be kind of explicit with my dependencies here. And so our virtual address space is going to rely on a couple of things. It's going to need to allocate frames for the page tables. It's going to need to do conversions between physical and and virtual addresses. So I'm trying to specify this really clearly here, and hopefully this might have some benefits if we ever try to unit test things. Maybe like in the way JOS does it, and the way like a lot of C projects do it, you might just have like global functions that you just call here, and that's just sort of like an implicit dependency. And here, all I'm doing is making it an explicit dependency, which is maybe kind of useful because then you can pass in, and we could convert this to an interface later if we wanted to, and pass in different implementations into the same one or something. Yeah. So, all right, and then maybe just to wrap it off for the day, need to implement map. Vpool, you are joined here at the actual end of the stream, unfortunately, but it's nice to see you. And just to kind of check this out, we have a nice clean build. And I don't know, what would we expect to see if we ran the kernel right now? I'm expecting that we're just going to see a panic need to implement map. Let's just go for that. And there we go. CR3, new physical pointer, PV header, and then bam, the address space map 29 need to implement map. So interesting. So yeah, I think that's kind of where I'm going to leave it today. That was an interesting stream. I'm not very confident in a lot of these topics, but we just made some baby steps, I guess, and now we're a little bit more well positioned to try to implement some of these virtual memory and page table functions. And then the idea would be that once we have some of these basic primitives for like mapping, querying, removing, we can decide how we want to use them. And we can either go with NSG's approach of manually re-implementing the Limine state of the virtual memory, or I don't know, we could consider trying to do my strange idea of copying the page tables, which is maybe a very questionable idea, but I'm sort of curious about it still. So, all right. Well, in that case, I'm going to leave it here. I'm just going to pop in. So here's the link to the Discord. Feel free to join the Discord if you are interested in this kind of content. And wow, we have 24 people in the chat. That's quite a lot, actually. So appreciate all the 24 people in the chat right now. I want to just directly ask you again, if you are watching this right now and interested and you are not subscribed, please smash that subscribe button. That is the easiest way to support my YouTube channel, and I would appreciate that quite a lot. So, word. All right, that's gonna be it for today, everyone. Thanks Ismail, thanks Chris, appreciate that vpool. I hope you have an amazing week. And actually, wait a sec, I need to I am going on a trip pretty soon, and so I will not be live for approximately 3 weeks. Actually, we're gonna do a bit of a November trip. I will be posting pre-recorded streams as usual every week, and I might be able to join the chat for some of them, but I'm doing a bit of a longer trip and I'll be away, so I won't be able to do a live one. So we'll have a bit of a different kind of November season, but that's just a bit of a heads up for everyone. So won't be doing these live ones, and I'll resume them in December. Okay. All right, that's it, everyone. Have a great week, and I will see you in December. Cheers.